In this video, we're going to talk about A*, probably the most famous algorithm in artificial intelligence. It's an old algorithm. It was invented by Nils Nielsen in the late 60s, but it's still really widely used and very important. So where do we stand? Last time we talked about minimum cost search. So this was an algorithm that guaranteed that we would be able to find the minimum cost path to the goal in problems where different actions can have different costs. So that's great. If all we're interested in is finding the best solution, we're done. We have an algorithm that'll do that for us. If we're interested in finding that solution efficiently, we might still have some work to do. So let's take a look at a scenario where our minimum cost search algorithm might get into a little bit of trouble. So here's a problem. This is our start state. Here's our goal state. And you and I, with our unfair perspective of this overhead view, can see that the shortest cost or the lowest cost path to the goal goes through here, and it's going to be 2. There's a second way to reach the goal, following this path of all of these 0.1s, followed by this 10 at the end. So by this point, you probably have a feel for what our minimum cost search algorithm will do when it's faced with this problem. This will go on the frontier with a cost of 1 to reach that point. This will go on the frontier with a cost of 0.1 to reach this node. And of course, minimum cost search always pulls the value off the frontier that has the lowest total cost. So that will be this choice. And the only additional reachable node from there is this. So we'll end up with this. And you see where this is going. With the sinking feeling, we start wandering off in this direction. To 0.5. And then at this point, we end up with this. Now we've incorporated the cost of that last expensive action, and our cost to this node in the frontier is 10.5. So we have 2 values in the frontier. At this point, we'll choose this one. We'll then look and see that we need to replace this 10.5 on the frontier with a 2. So we would end up with this. And the next value that will be removed from the frontier will be this 2, and that now points back this way. So we've found the minimum cost path. It goes along this route as we knew it would. But we had to go down the garden path here before we got there. So that's too bad. To some extent, it's unavoidable, right? The algorithm doesn't know what we know. It doesn't know what's coming. But wouldn't it be great if it did? So the way this algorithm works is it has access to some cost function, right? And we'll interpret this as the total cost, the total minimum cost to reach a particular node in the graph. Wouldn't it be great if we had something like this? We'll say O for optimal. What we would really like to know is the cost to reach a particular node in the graph plus the amount that it's going to cost us to get from that point to the goal along the shortest possible path from that point to the goal. If we know this, then it becomes a lot easier to choose an option because we're going to be able to look not just backwards at how long it took us to get to that point in the graph, but we can also look forward. How long is it going to take us from this point onward? So what would that look like if we had access to this value? In this case, the frontier might look like this. 10.5 and 2, right? 10.5, where did that come from? Well, it's this backwards-looking cost of 0.1 to get to this node, plus this forward-looking cost of 10.4 to get from this node to the goal. And similarly for this node. So now, right, life is easy for our algorithm. It clearly wouldn't choose this one. It would choose this one, and we're guaranteed to work our way directly to the goal along the shortest path. So this is brilliant. Why didn't we do this earlier? The reason we didn't do this is that, in general, we don't have this value. Usually, the only way to know the optimal path cost from a node in our graph to the goal is to actually know what that path is. And if we already know what the path is, obviously we don't need to run an algorithm. So we don't have this, but it would be nice if we could somehow make use of this intuition, this idea of looking forward in the graph in addition to looking backwards. And that's the idea behind A star. And the simple idea is that, well, we don't have this, but maybe we have some estimate of that, which we'll generally call H for heuristic. So heuristic is meant to indicate that it's not exact, but it's some sort of reasonable guess about how long it might take us to get from node N to the goal. So let's look at an example from our textbook down at heuristic search. So here's an example heuristic function. So this is coming from that robot delivery example that we saw earlier. Let's look back at that. So here's that office environment, and remember the goal of the robot here is to reach room 123. So the idea behind that heuristic, so it's complicated to figure out the actual shortest path from a particular location in this environment to the goal, right? We have to figure out where we can go through doors and where the hallways are, so that's the problem we're trying to solve. But it's not very difficult to figure out the straight line distance between any point in this map and the room that we're trying to reach. If we want to accomplish that, all we need to do is lay a ruler down on the map and measure how far it is. So in that case, our heuristic is going to be built on the assumption that we just sort of pretend for a moment that the robot can walk through walls and go straight to the location that he's trying to reach. So that can be helpful information, right? That tells us, for example, that if we are choosing between somehow 0119 and male, 0119 looks a lot more promising. In a straight line sense, it's closer to R123 than male is. Of course, it can also be misleading, right? If we're using that heuristic to decide between C1 and B4, C1 looks really good. In a straight line sense, it's quite close to the goal, whereas B4 is a long ways away in this straight line sense, but in terms of the number of actions, it's closer. So our heuristic doesn't need to be perfect. It probably can't be perfect, but it should be helpful. And importantly, it needs to be an underestimate. So as long as it's an underestimate, we're guaranteed that we'll still actually find the correct answer. So there's no real advantage to finding poor solutions quickly, right? We want to maintain our guarantee that we're going to find the optimal solution, and the goal of A star is to be able to do that more efficiently. So why would it matter if our heuristic overestimated the cost to goal? Let's see what could go wrong there. Let's say that our heuristic function here for this node is 20. So that's an overestimate. The actual optimal cost from this node to the goal state is just 1. So that's a terrible overestimate. So that means that if we're using the cost to that point plus the cost from our heuristic from that point as our value that we're using to maintain our priority queue, we would have a 21 there. And we don't know what this heuristic is. Maybe it gives us a value of 0.1 for the rest of this route, which obviously is an underestimate. But so we'll expand. Eventually we'll reach this point with a path cost of 10.5. 10.5 will be removed. We'll believe that we found the shortest path to the goal because we never explored beyond this point. Our overly pessimistic heuristic estimate made this seem more unappealing than it should have been. If this had been an accurate estimate or an underestimate, at this point 10.5 would have been larger than the value here, so we would have ended up finding the correct path to goal. So that's why the estimate has to be no larger than the true path to cost of the goal. So what is the A star algorithm? I haven't actually made that clear yet, but we know already A star is exactly the same as the minimum cost search algorithm that we saw before. Somewhere here. Oh, here we go, A star search. Here's the complete description of the difference. A star is implemented by treating the frontier as a priority queue ordered by f of p, where f of p is the sum of that cost plus the heuristic. So exactly what I did here. So there's no need to show another algorithm. We've already got the algorithm. The only difference is that we use this sum rather than the path cost so far. So the implementation differences between minimum cost search and A star are trivial. The tricky bit is to come up with an admissible heuristic that does a good job of making the algorithm more efficient.